Qazi Talha, and I am representing the team Dark Bulls. The project that we've been working on for our data structures course is data compression. Now, data compression, as we all know, has become a very integral part of modern day computing, and this is because it allows us to conserve space and it allows us to transfer data at a more efficient rate. The idea behind data compression is, of course, to reduce the file size of any text or data file. And the main example that we're going to look at today and the application that we've implemented is text data compression. When it comes to text data compression, it is known as lossless text compression. Lossless text compression means exactly how it sounds. It is to reduce the file size of a text file without modifying or changing any of the original data. How do we do that? Well, we're going to use a splay tree, which we've modified into a cumulative tree. This the splay tree was the data structure that we've been given, and use modifying into a cumulative frequency tree. What we're going to do is we're going to use an algorithm known as Huffman coding, and this text compression algorithm, what it does is that we're going to, let's take an example. We're going to take a string of characters. Let's assume that the string is n space a. Now these are four characters. We're going to insert these characters one by one into our cumulative frequency tree, as you can see on the right of the screen. And once you've done inserting all of these characters, you're going to see that they've been added with reference to their frequency. So if A has been occurred twice in the string, it's going to have a 2 beside its inside its node, right? So of course, since this is a splay tree, what it's going to do is it's going to splay it. So the final tree that we receive is going to look like this. Now, the idea behind the Huffman coding is that you're going to encode every single leaf node within this tree, because every single leaf node represents a character in the original text file. And you're going to do this by traversing right. By whenever you traverse right, you're going to add a 1, and whenever you traverse left, you're going to add a 0. This will give you a specific code for every character with reference to from the root towards the leaf node, and with reference to the sequence of ones and zeros that you take to reach the leaf node. So when you convert our string NA, you're going to get 0, 1, 0, 1, 1, 0. Now this is 6-bit long, whereas our original text was 32 bits long. You already know that this has been compressed. How do you decompress it? Well, the same way. You go down the cumulative frequency space tree, and you as soon as you hit a leaf node, you replace the sequence of bits with the character. Another thing that we do in order to make this more efficient and more useful is that we convert the encoded bits back into ASCII in combinations of 8. We use pair of 8 bits, and then we convert them to ASCII so that this ASCII is very reduced compared to the original file. Now let's take a look at an example. So let's take a look at this file. And this file is, of course, a large amount of words and characters. What we're going to do is we're going to use our compression algorithm, and we're going to generate two new files. We're going to generate a compressed file and a decompressed file, right? So this is the compressed file that we've generated through our algorithm. Of course, it sounds like a lot of gibberish. It doesn't make sense at first look. This is because it has been converted back into ASCII, so it doesn't make sense right now. But when you decompress this file, what you get is the original data back, right? So let's take a look at these sizes. The original file was around 77 kilobytes, while the compressed file was around 57 kilobytes, and of course the decoded file was back to the original. Now this reduction of 20 kilobytes is close to the ideal amount of reduction that you get in lossless text compression. By close to, I mean that of course there are some limitations. Let us take a look at these limitations. There are compression algorithms that are better adaptations of the Huffman encoding, and these are the Huffman adaptive Huffman and Huffman encoding with reference to more 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 combinations of uh, more combinations of strings, and through these specific modifications, we can of course increase the amount of compression, as you can see in this table below. Uh, this increase in the text compression will allow you for a smaller file size than the original. However, as a proof of concept and as a use of Splay, the algorithm that we've built is fairly good when in comparison to other encoding and compressing algorithms. Thank you.